The overall conviction among most researchers is the theory of the universe's origin, which remains as the main clarification for the starting points of the universe. It envelopes the making of stars, planets, and all life on those planets, counting ourselves. Notwithstanding its fairly unconventional name, the Big Bang offers a clear look into what could have happened at first. The universe was dense into a brief space, more modest than a pinhead, with particles thickly pressed. From this tiny point, an epic blast of issue followed, known as the enormous detonation. This event, happening billions of years ago, set the stage for the unfurling of infinite history. Anyway, advancements in logical information have prompted increasing inconsistencies with the forecasts of the theory of how things came to be. When NASA launched the James Webb Space Telescope, the largest and most progressive space science observatory ever developed, researchers guessed that its observations would reinforce the theory of prehistoric cosmic detonation. Lamentably, after only 1 year in space, the telescope has flabbergasted science with its exceptional capacity to peer deep into the universe's past. The James Webb Telescope's surprising abilities have revealed worlds tracing all the way back to a period so old that it challenges our comprehension of the universe's beginnings. This discovery has ignited an intense investigation into what existed before the Big Bang. One vital moment in this journey happened when astronomer Rohan Nu, working with data from the telescope, accidentally found a galaxy going back only a short time after the Big Bang, making it the oldest universe ever seen. This discovery sent shockwaves through mainstream researchers, highlighting the groundbreaking capability of the James Webb Telescope. Its mission to change our cognition of the universe has only just begun, promising to uncover exceptional insights into the earliest sagas of the universe's presence. This epic, hardly investigated before, holds the key to figuring out the development of the first stars and galaxies. The telescope's discoveries have challenged introductory assumptions, revealing galaxies with attributes outperforming past expectations. This surprising overflow of early galaxies has sparked a whirlwind of scientific inquiry, testing analysts to accommodate these observations with existing theories. As researchers wrestle with these revelations, they face significant questions concerning the crucial nature of the universe and the forces shaping its advancement. Moreover, the James Webb Telescope's technology is revolutionary, positioned 1.5 million kilometers away from Earth, safeguarded from earthly interference and cooled near absolute zero by its tennis court-sized sunshield. The telescope carries a giant, segmented mirror and exquisitely sensitive instruments designed to reveal details of the enormous first light never before seen. This epoch, known as Infinite Dawn, happened something like a few 100 million years after the Big Bang, marking the period when the first stars and galaxies began to form. The process of how this unfolded remains a subject of intense review, with hypotheses ranging from the effects of dark matter and dark energy to the interactions between starlight, gas, and dust. The telescope's observations of galaxies from the Big Sunrise offer an interesting opportunity for cosmologists to test their understanding of these critical phenomena. By examining these ancient galaxies, researchers can either confirm the validity of their current models or reveal gaps in understanding that could lead to significant new discoveries. At first, it was projected that the telescope would find only a few weak and small galaxies in its pilot studies. However, the reality has far surpassed these expectations. The telescope's very first pictures of the distant universe uncovered numerous worlds with ages, sizes, and luminosities that outstripped all expectations. This unexpected abundance of early galaxies has triggered a race among space experts to claim new records for the earliest known galaxies. Every day brings forward claims of yet another record-breaking discovery, leaving the academic community in awe and prompting a reassessment of our understanding of cosmic history. In the wake of the James Webb Telescope's discoveries, scholars and onlookers have scrambled to make sense of the presence of these suddenly encountered early universes. Some speculate that flaws in the analysis of the telescope's initial observations might be responsible for these atypical discoveries. However, the consensus remains that these findings represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic advancement. The new discoveries from the James Webb Space Telescope concerning early galaxies raise significant questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some researchers speculate whether these observations can be accommodated with existing theories, others propose that they may be the first signs that the universe is even more complex and particular than previously envisioned. The question isn't anything less than our fundamental understanding of how the ordered universe we know emerged from primordial chaos. The early discoveries of JWST have the potential to rewrite the initial chapters of cosmic history, shedding light not only on distant stories and far-off galaxies, but also on the very existence of our own Milky Way galaxy. As Mark McCarran, a senior consultant for science and investigation at the European Space Agency, puts it, "You build these machines not to confirm the worldview, but to break it. You just don't know how it will break." The origins of JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At that time, G. Waite, then Deputy Director of SSI, was tasked with imagining what might come after Hubble. Despite initial reservations, Waite and a small group began laying the groundwork for what would ultimately become the next-generation space telescope, later renamed JWST. Unlike Hubble, which primarily observes visible light, JWST was designed to see in the infrared range, allowing it to peer much further into the universe. This capability is crucial for studying early galaxies whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its huge, cold, star-like mirror, JWST became the best tool for unlocking the secrets of cosmic dawn. The need for JWST was highlighted in 1995 when the Hubble Deep Field observation revealed a plethora of galaxies in what was thought to be an empty patch of sky. This discovery underscored the richness of the early universe and confirmed the importance of a telescope capable of probing even deeper into cosmic history. After more than 2 decades of development and at a cost of around $10 billion, JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of scientific observations. Early projects like the Cosmic Evolution Early Release Science Review and the GRISM Lens Amplified Survey from Space were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded predictions. JWST's observations have challenged existing ideas about the early universe, revealing galaxies that defy conventional models. These surprising discoveries highlight the importance of pushing the boundaries of scientific investigation and underscore the extraordinary potential of cutting-edge advancements like the James Webb Space Telescope. As researchers continue to unravel the mysteries of the universe, they are poised to transform our understanding of cosmic history and the forces that have shaped our universe into what we see today. The early observations made by the James Webb Space Telescope have shocked space experts by uncovering extremely distant galaxies, much earlier than expected. Before JWST, the most distant known galaxy was GNZ 11, found in 2015, with a redshift of 11, corresponding to a cosmic time of around 400 million years. However, from the start of the JWST observations, the GLASS team, led by Rohan Nu and another independent group, made an extraordinary discovery. They identified a galaxy named GLASS Z13 at a redshift of 13, about 70 million years earlier in cosmic history than GNZ 11. The rapid speed of these discoveries was facilitated by improved techniques for measuring redshift, which, while less precise than direct measurements, provide a quick estimate of a galaxy's distance. Surprisingly, GLASS Z13 appeared unexpectedly bright and massive, already containing a stellar mass equivalent to billions of suns, despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing discoveries. Many galaxy candidates with estimated redshifts as high as 20 emerged, indicating their existence just 180 million years after the Big Bang. Some of these galaxies displayed complex structures, a feature not expected to appear so early in cosmic history. Moreover, evidence arose for galaxies similar in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenged the predictions of the standard cosmological model, Lambda CDM, which describes the universe's evolution based on our understanding of dark energy and dark matter. The formation of massive galaxies in the early universe presents a significant puzzle for cosmologists to solve. To understand this challenge, it is essential to examine the early stages of the universe's evolution. In the first seconds after the Big Bang, the universe was a hot and dense soup of primordial particles. Over millions of years, the first stars began to form, creating the building blocks for galaxies. This process of massive development, from chaotic beginnings to the organized universe we observe today, is believed to have taken about 1 billion years. JWST's observations challenge this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing various small protogalactic fragments merging to form larger galaxies, as predicted by current models, JWST has identified galaxies that are already sizable and luminous. Observations with instruments like the Atacama Large Millimeter Array in Chile have provided additional evidence supporting the reality of these distant galaxies, ruling out the possibility of low-redshift intruders. These pivotal discoveries open new avenues for understanding the early universe and may require modifications to our current cosmological models. JWST continues to disrupt our understanding of cosmic history, challenging our biases and pushing the limits of cosmic investigation. The absence of visible dust in the observations made by the Atacama Large Millimeter Array highlights the difficulties faced by telescopes in confirming observations made by JWST's advanced capabilities. As Rohan Nu noted, while JWST can cross-check its own observations, ALMA's difficulty in identifying the galaxy underscores the complexities of confirming such discoveries. The implications of JWST's observations are significant, potentially challenging the standard LCDM cosmological model and necessitating corrections. Michael B. and Kulin expressed astonishment at the results, suggesting a major departure from our current understanding of cosmology. One controversial theory that could explain these findings is modified Newtonian dynamics, which challenges the existence of dark matter and proposes alternative explanations for observed gravitational effects. JWST's observations align with this theory, according to supporters like Mark MCLO, who sees this as further evidence supporting the hypothesis. However, skepticism remains among some researchers, such as Joss Arapi, who point to the difficulties in reconciling M with existing data. On the other hand, the absence of dust in early galaxies could provide a simpler explanation for their brightness, possibly explaining efforts to measure their masses accurately. Andrea Ferrara suggests that dust may not have had enough time to form in the early universe, or it may have been stripped away during galaxy formation. Charlotte Artisan and her colleagues propose that JWST may be detecting the brightest young galaxies, which are easier to observe. David Spergel suggests that intense high-mass star formation in the early universe could explain the observed brightness of these galaxies, hypothesizing that early magnetic fields may have played a role in triggering star formation. This offers a potential explanation for the rapid rise of galaxies in the early universe. The rapid flow of scientific papers emerging from JWST's initial observations underscores the importance of these discoveries and the significant implications they hold for our understanding of cosmology. As researchers continue to analyze JWST data, they may uncover further insights that test and expand our understanding of the universe. When the first data began streaming down from the James Webb Space Telescope, astronomers were eagerly awaiting the results. Many had been working on their data analysis pipelines for months in preparation. Instead of following the traditional peer review process, which can often take months, space experts chose to publish their findings on AR14, a site where scientific papers can be uploaded with minimal review by mediators but well before formal peer review. This approach allowed a new form of peer review to unfold almost in real time on platforms like Twitter and other social media channels. Rohan Nu describes it as science by AR14, and the subsequent frenzy of discussion was intense and surprising. Nancy Levinson, the interim director of STSI, admits underestimating the extent of the activity. However, there are concerns about the potential downsides of this rapid dissemination of findings. Klaus Horst, JWST project researcher at SSAI, notes that while the quick sharing of results allows for speedy publication and conversation, there's a risk of rushing the process. He stresses the importance of the gold standard of refereed peer-reviewed papers. Early calibration issues with JWST have been identified, potentially affecting some results. Nathan Adams of the University of Manchester and his colleagues found dramatic changes in redshift values for certain galaxies after recalibration. These challenges highlight the need for caution and careful analysis. Despite these difficulties, space experts remain excited about the discoveries made by JWST.